If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Capital Isn't. Capital Isn't uses the latest economic thinking to zero in on the ways that capitalism is, and more often isn't, working today. Join Vanity Fair contributing editor Bethany McLean and distinguished professor of economics Luigi Zingales as they explain how capitalism can go wrong, and what we can do about it. Listen to Capital Isn't, part of the University of Chicago podcast network. What if I told you that trillions of invisible ghost particles from space are passing through your body right this second? Would you believe me? Well, it's true, and these ghost particles are called neutrinos, and they're not only invisible to us by eye, they almost never interact with matter, and so they're very, very hard to detect at all. But it turns out that from the tiny fraction of times that we do manage to catch neutrinos, we can use them to learn a lot of new astronomy.
It's a beautiful idea, and we can see places in the universe that light can't reach us from. For the same reason they're hard to detect, they're also hard to absorb. So like deep in the hearts of galactic nuclei next to big supermassive black holes that the light can't escape from, we can see the neutrinos. In the cores of massive stars that are undergoing collapse, the light can't reach us, but those neutrinos can. So we can probe parts of the universe using neutrinos that we can't with any other kind of cosmic messenger.
So today we're talking all about neutrino astronomy. How does it work? What do these particles reveal to us about the otherwise invisible reaches of the universe? And also, what do they reveal to us that we can't yet explain? You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So I just want to open by saying neutrino astronomy has a certain kind of nostalgia in its power to me. When I was a bushy-tailed, bright-eyed grad student, being exposed to all these cool ideas for the first time, my first projects were all in neutrino astronomy. My PhD advisor was this guy named Francis Halzen, and he was the head of the Amanda experiment at the time and later would become the head of the IceCube experiment. And he was a theorist, but he still, he and I did theory related to what these neutrino telescopes would be able to do, talking about stuff like very high energy neutrinos from very exotic sorts of astrophysical environments. So I still feel a sense of excitement about this topic, even though, I only occasionally work on it now, a little bit, just only occasionally now.
Okay, so before we talk about neutrino astronomy, let's back up and talk a bit about traditional astronomy. If you think of your classic astronomer, you may imagine someone looking up at the night sky with some big telescope made of mirrors and lenses, which magnify faraway images of planets and stars and things like that.
And, 100 years ago or something, that was mostly true. Almost all of astronomy that was being done a century ago was done using visible light or photons in this kind of range of wavelengths that your human eye can detect. So this is roughly 400 to 700 nanometers. So, just under a millionth of a meter in wavelength.
But these optical photons, the light that we can see, is not all of the light in the universe. It turns out that light comes in a whole range of wavelengths that stretch way beyond the limits of what our eyes can observe. We call this entire range the electromagnetic spectrum. It includes optical light, sure, but also light with much longer wavelengths, like infrared and radio waves, and light of shorter wavelengths than we can see, like ultraviolet, X-rays, and gamma rays. So yes, your car radio, your microwave, the X-ray at the dentist, these things are all emitting light. It just so happens that it's light we didn't evolve to see with our eyes. But we can build different kinds of telescopes that can see this light. And once we discovered that, a whole new world of astronomy became possible. We were able to see things in the universe that were once completely invisible to us.
So all of these different kinds of light help inform astronomers about their universe and what they're looking at. But there are things that you can't learn from light alone. So photons carry a lot of information, but other things travel across the universe, and we could detect and we can learn things about our universe by studying them as well. So, like, let's say some energetic electrons are traveling from out in space, hitting the Earth. We can learn things about the universe by studying those electrons. And we can do the same thing with protons. We call energetic protons and electrons traveling through space cosmic rays. And we can also look for things like antimatter versions of cosmic rays, like positrons and antiprotons. Recently, astronomers have been using things called gravitational waves to learn about, for example, how black holes and neutron stars merge and things like this. And what we're going to talk about today is a different kind of particle that travels through space and can be produced in a wide variety of astrophysical environments that we can use to learn different things than light or gravitational waves or cosmic rays teach us. And these particles are what we call neutrinos. Neutrinos are a wholly different kind of object than the sorts of matter that you might regularly think about. Neutrinos are super, super light particles. They're more than 1 million times lighter than the electron, which, other than the massless photon and gluon, the electron is the lightest particle we know about. So this is more than 1 million times lighter than that. And they're super feebly interacting. So an individual neutrino that's flying towards the Earth will, in all likelihood, travel straight through the Earth without even noticing it's there. A very, very small fraction of neutrinos will interact with matter as it passes through it. In fact, Shalma, this was our very first research project together. Mm-hmm. If you recall, I'm sure you do. Yep. You calculated how ultra-high energy neutrinos would behave as they pass through the Earth.
So most neutrinos coming from space fly straight through the Earth as if it wasn't there. For a neutrino to interact with an atom in the Earth, and for us to be able to detect it, it has to be extremely energetic.
I think it's in the ballpark of a few hundred tera electron volts, so like way more energy than even the LHC accelerates particles to. And the reason for this is that the neutrinos don't carry any kind of electric charge, so they don't feel the electromagnetic force. And they don't carry anything that we call QCD color, so it doesn't feel the strong nuclear force. So the only forces that act on neutrinos are the weak force, which by its, because of its name, obviously it's very, very feeble. And then the force of gravity, which is even less strong than the weak force. So for the most part, neutrinos travel straight through the universe without experiencing any kind of interactions at all.
But of course, knowing us physicists, we are still going to go looking for those few neutrinos with just enough energy that they do hit the Earth.
Using neutrinos to do astronomy has a long history. The first step in that direction, I think you could say, took place in the 1960s when physicists started to detect neutrinos that were being created in the Earth's atmosphere. So the idea here is that protons would, with a lot of energy and speed, high velocity protons called cosmic rays are just bombarding the atmosphere all the time. And some of those particles collide in the atmosphere in ways that produce neutrinos. And then those neutrinos come down to Earth. And in principle, you can detect them. But I would say from an astronomer's perspective, these neutrinos aren't super useful. The cosmic rays that are bombarding the Earth come from all directions, pretty much isotropically or equally in all directions because of the impact of magnetic fields. So we're seeing all these neutrinos, but they kind of come from everywhere and they don't point at anything. So I don't think you can do a lot of astronomy with them. What's more interesting from a neutrino astronomy perspective are the neutrinos that might be produced in the nuclear reactions that take place inside of stars. So, for example, in our sun, the sunlight is being created, or the energy that the sun has is being created when protons fuse together to make helium nuclei. So 4 protons join together and are converted into a helium nucleus, which has 2 protons and 2 neutrons in it. So in this process, 2 of those protons have to switch their identity and become neutrons. And in that process, they release a pair of neutrinos. So This is happening a lot in the sun. I want to emphasize this is like a very, very high rate of nuclear fusion is going on all the time in the sun. And this means that something like 10 to the 38 neutrinos are being radiated from the sun every second. And that means here on Earth, if you have 1 square centimeter, just that neutrinos can pass through, and you can measure all those neutrinos, you'd find there'd be about 100 billion of them passing through that square centimeter every single second. They're just constantly passing through your body, trillions every second of every day, and they just don't notice that you're there because they're so feebly interacting. So this gives neutrino astronomy a challenge and an opportunity. On the one hand, it's really hard to detect the neutrinos, so you need really big and powerful detectors to see the neutrinos. But on the other hand, you can see neutrinos that can come from places that other stuff can't come from. So like, let's say you want to study the very core of the sun. When a neutrino is released into the core of the sun, it just passes straight out. And we observe it, we can measure it, we can see the inner workings of the sun in this way. Light can't do that. If you deposit a bunch of light in the core of the sun, it like bounces around off of other matter inside the sun. It takes a really, really long time for it to slowly scatter outward. And by then it's erased most of its information.
This is because light interacts with the electromagnetic force, but neutrinos don't.
Really, light allows us to tell what the surface of the sun is like, whereas neutrinos allow us to understand what's going on in the core of the sun. The first neutrinos from the sun were detected in 1968 by Ray Davis and John Bacall and their group. This was something called the Homestake experiment. They used 100,000 gallons of, I have to see how to pronounce this, perchloroethylene, I think. It's a fancy way of saying dry cleaning fluid. If I were a chemist, I would just know this. But this was all instrumented a mile underground in this gold mine in South Dakota called the Homestake Mine. At the time, it was still a real active gold mine. Today, it's just a science laboratory. But they had this huge underground detector. They could detect those neutrinos from the sun and really begin to study the inner workings of the sun. So nuclear reactions make neutrinos not only in stable stars like the sun, but especially when stars explode as supernovae. Unlike the sun, which makes a steady kind of outgoing flux of neutrinos every moment of every day, when a star explodes as a supernova, it makes a burst of neutrinos. So it's a lot of energy, and these can be detected from much greater distances than the sun. And so far, we've detected neutrinos from exactly one supernovae, and it happened in 1987. We call this supernovae 1987A. And a handful of neutrinos were detected from this object using a variety of instruments around the world. They weren't really even looking for neutrinos. It was just something they kind of got to do as a side gig. So that was really the very first opportunity for astronomers to study an object with neutrinos outside of the boundaries of our own solar system.
So detecting these solar neutrinos is super cool for its own sake. We get to realize that all this theory about these invisible particles, it really is true. But neutrino astronomers want to use neutrinos in a bigger way. They want to use it in a way analogous to the way past astronomers used light. And in order to detect enough neutrinos to do that, we need way bigger detectors.
And people started to build these detectors or design these detectors as early as the 1970s. So there was this underwater neutrino telescope called Dumond in 1976 off the shore of Hawaii. And then there was a Lake Baikal telescope that started in 1980 in the Russian Lake Baikal. And these experiments continued into the 1990s. And around that time, the first ice-based neutrino telescope called Amanda was started to be built. This was just off the South Pole, basically burying a string of detectors deep inside of the Antarctic ice, hoping to detect neutrinos as they pass through that instrumented volume of ice.
Why are physicists freezing their neutrino detectors in the Arctic ice? Well, since neutrinos make such a subtle signal, you want to be really sure that what you're seeing in your data is actually a neutrino, and not just some of the many random background particles that are going about their business in the atmosphere.
Absolutely. And the deeper you go underground or underwater or under ice, the quieter these environments will be. and the more likely we'll be able to isolate the real signal from all the noise of cosmic radiation that comes and strikes the surface of the Earth all the time. So in these neutrino telescopes, they really work by just amassing huge amounts of volume that if a neutrino interacts in that volume, you'll be able to tell, be able to detect that sort of interaction. So like, for example, in an experiment like Amanda, that first Antarctic experiment, the idea is a neutrino would come along and it would most of the time pass through without doing anything. But, 1 out of a million or 1 out of a billion times, it would interact and produce something called a muon.
Muons are basically the cousin to the electron. They are almost identical, except a good amount heavier. And as an electrically charged massive particle, muons are way easier to detect directly than neutrinos.
That muon will just plow through the detector, putting off light and radiation and energy in all directions. And all of those detectors that you buried in the ice, you can use those to detect that muon track, infer the presence of the neutrino, and figure out what direction it came from, and also measure its energy.
So with these neutrino detectors, we're actually directly seeing the muons and using them to infer the existence of the neutrinos that came before.
So I was actually a grad student at the University of Wisconsin during the Amanda era. So when they were working on this instrument, and my PhD advisor at the time was this guy, Francis Halsen. He was a PI or principal investigator of Amanda. And he and I were theorists, but he was leading an experiment. So we were doing all this theoretical work related to what a telescope like Amanda or other even bigger neutrino telescopes could potentially see. We were thinking about exotic astrophysical applications and what kinds of cosmologically interesting objects could exist out there that could make the kind of neutrinos that a telescope like this could potentially see. So it turns out that, these experiments I've talked about, like Demond and Lake Baikal and Amanda, all did some interesting stuff, but none of them were really big enough to do what I would call neutrino astronomy. That really kicked off with the IceCube Neutrino Observatory, which was constructed between 2005 and 2010. It's just a much bigger and better version of the Amanda telescope. It has 86 separate strings of cable, each about 1 kilometer long, and they're all buried deep in the Antarctic ice. So to bury something in Antarctic ice, you have to use a hot water drill, and it goes down several kilometers, and then in the water that you've melted the ice into, you deploy these strings and then let the water freeze again.
So these strings are frozen underwater?
Yeah, you can't keep the water thawed. It would just take too much energy.
I don't know why I didn't realize that. I thought that the strings would be like in some kind of like machine that was like a vacuum or something.
Not at all. So they're like 1 meter diameter holes roughly, and they melt that hole going a few kilometers down. They put the string in there, and then it freezes in place. I think if I remember right, in the Amanda era, one of them froze before they could get it all the way down. And it was like an engineering debacle, but
that's interesting.
Yeah. So all being told, IceCube has about 5,000 of these detectors scattered around a volume of about a full cubic kilometer of ice. That's huge. And neutrinos pass through it all the time. Even though only a small fraction of them interact, that's enough for them to actually begin to detect these what we call muon tracks, like I talked about before, and other kinds of neutrino-caused events, like big things we call cascades and showers, and even like more exotic kinds of events that go by clever names like double bang events and lollipop events and things like this. So in 2013, the IceCube collaboration announced that they detected the first clearly astrophysical high-energy neutrinos. These were the highest energy neutrinos that had ever been seen at this time, and they named them Bert and Ernie after the Sesame Street characters. They have this habit. They later detected others that they called Big Bird and other sorts of Sesame Street characters. These, I can't emphasize enough how much energy these particles carry. They have each about a peta electron volt of energy, or put in other words, about 1,000 tera electron volts of energy. To put that in context, the Large Hadron Collider, the most powerful particle accelerator physicists have ever made, only reach collisions of 14 teraelectron volts. So this is much more energy than we can study in any of those man-made laboratory environments. These three events have since been just the tip of the iceberg, if you excuse the pun, of what IceCube has been able to detect. In this first decade of its operation, it's detected lots of neutrinos, ranging all the way from 10 petaelectron volts or so, all the way down to the lowest energies they're sensitive to. We still don't know where these particles are coming from. They kind of come from all directions, which tells us that they're not coming from sources distributed in the Milky Way, but from beyond the limits of our galaxy. But we still don't know what kind of objects or environments create these neutrinos, and that's kind of the big open question for the science of neutrino astronomy. So we have a bunch of guesses for what might make neutrinos like this out beyond the confines of the Milky Way. One of the earliest guesses, which, by the way, my first couple of scientific papers were on, are objects called Gammaray Bursts. So these are big flashes of gamma rays. That's where they get the name. But we now understand that Gammaray bursts are caused when particularly large stars collapse to make a black hole, or in the mergers of neutron stars, again resulting in the formation of a black hole. We thought back, when I was a grad student, that all the gamma ray bursts in the universe might make enough neutrinos that would produce, 10 or 20 signals every year in an experiment like IceCube. But that doesn't seem to be the case anymore. We see neutrinos in IceCube and we see gamma ray bursts, but those neutrinos aren't arriving at the same time that those bursts of light are being observed. So they don't seem to have anything to do with each other. So, maybe gamma ray bursts still do make neutrinos, but they're not the main source, at least it seems that way, of what IceCube is seeing. Another really popular idea are that these supermassive black holes in the cores of certain galaxies are really doing a lot of active stuff. They're sucking in matter, accreting matter, and creating these giant, powerful jets of energy that shoot out along either axis. And in 2018, the IceCube collaboration announced that they had actually detected a particularly high energy neutrino from the direction of one of these active galactic nuclei, one of these supermassive black holes. This particular black hole is called TXS 0506 plus 056. It's a very romantic name, of course.
Yeah, sounds like Elon Musk and Grimes' child.
I don't know that particular pop culture reference, but did Elon Musk and Grimes name their child a bunch of numbers and letters?
Yeah, pretty much.
All right. Okay, so another possibility are these things called active galactic nuclei. They might be the source of these neutrinos. So what an active galactic nuclei is a very big black hole with masses of millions or billions of times as much as the sun. And these things can be doing complicated things to their environment, accreting matter, and taking that energy and firing it out as what we call jets, these powerful expulsions of energy along the axis of their galaxies. And in principle, these things could accelerate cosmic rays up to very, very high energy and making a lot of neutrinos in the process. And this has long been a big candidate for an experiment like IceCube to look for. And then in 2018, IceCube announced that they'd actually detected an extremely high energy neutrino from the direction of a particular AGN, or active galactic nuclei. This particular AGN is about 6 billion light years away, and one of its jets is pointed right in our direction. So we're looking down the barrel of this particular AGN. And furthermore, it's a really variable source. It gets bright and gets dim, from month to month and year to year. And this neutrino happened to have arrived during a period where it was actively flaring. For all these reasons, people got really excited and think that they might have detected the first real source of these neutrinos. Now, personally, I'm kind of skeptical of that conclusion. I think the statistical significance isn't what I'd call overwhelming. It's pretty hard to write down a theory, not impossible, but pretty hard to write down a simple theory that explains why an object like this would make a detectable neutrino flux. But, maybe I'm wrong and maybe this is the right answer. I think in the future we'll be able to figure this out, though, with telescopes like IceCube and whatever follows. So the third big category, along with Gammaray bursts and active galactic nuclei, of things that might make a signal that IceCube could see, is that somehow this is connected with the process of the formation of stars. So it's pretty widely believed, or nearly universally believed among astrophysicists, that the relics of supernova explosions accelerate protons and other nuclei up to very high energies, up to peta-electron volt energies. And then these things could collide with gas and make observable fluxes of neutrinos, observable numbers of neutrinos. So the question really isn't if this happens, but really how many neutrinos are made this way. And do they make up a small fraction of what IceCube is seeing, or a large fraction, maybe the bulk of what IceCube is seeing? The real challenge here is that there are so many galaxies out there that are actively making lots of stars right now. Any one galaxy will produce one or fewer neutrinos that IceCube will see. So you won't ever be able to see an individual galaxy in this way. What you'll see is a whole sky filled with individual neutrinos, all from different galaxies. After all, there are a trillion galaxies in the observable universe. We don't see nearly that many neutrinos. And it would be really hard to ever know for sure that this is what's going on. So this is going to be hard to do, but maybe with bigger telescopes, with better angular resolution, we could actually sort this out in the years and decades ahead.
Why This Universe is brought to you by the University of Chicago Podcast Network. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.